Streaming?
Yes.
All right. Okay. Right. Yes. So, welcome everyone. Welcome everyone to our new series within the IEEE Graduate Student Chapter. Series is about getting to know our professors within ECE and within UT Austin in general. So today, and we're actually happy. So this is actually the first lecture series within this, the first lecture within the series, and we're really happy and honored to have with us today Professor Marculescu, who is actually, probably needs no introduction for the ECE folks, since she is the department chair of the ECE of the UT Austin. And I could give a long list of achievements and academic pathways, but it would be just a spoiler to the talk, which is pretty much the reason for the talk. So I'll just leave it to Professor Marculescu, and welcome, and the floor is yours, the online floor.
Okay. Thank you all for attending, and thank you for inviting me. I'm really delighted to be here. And like Dimitri said, I'm a professor and also the chair of the department. I actually joined very recently, well, relatively recently, less than a year ago, last December. So, so I'm happy to tell you a little bit about my career, and the reason my talk is titled "Confessions of an Accidental Engineer" is because I did not set to become an engineer, but I ended up one. And I think I'm in the best place now. ECE is probably at the intersection or the best intersection of computing, electrical engineering, and computer science altogether. So I think ECE is a broad discipline and a really unified discipline that is really offering many people, including me, a very rewarding career. Just a little bit about me and how I started. And feel free to interrupt me anytime. I'm happy to answer any questions or tell you more. So I'm originally from Romania, from Bucharest. So if you can see the map here, I'm from the capital of the country, Bucharest. And for those of you who might know, there are other famous Romanians. I'm not that famous. I come from the same country as them. And some of them you might know, some of them you may not, but I just picked three. So Nadia Comaneci, she's I guess she was the first gymnast who ever got a 10, a perfect score in gymnastics. Constantin Brâncuș, he's actually a well-known sculptor, especially in Europe, but if you go to Philadelphia Museum of Art, you can see some of his sculptures. And of course, Prince Dracula, who inspired the Bram Stoker's novels. He wasn't as bad. I guess he was as bad as people were in those times. But anyway, so I lived in Romania for 25 years and then moved to US. And the way I ended up where I am, so like I said, I grew up and went to college in Romania. I got my undergrad degree in computer science at the Polytechnica University of Bucharest. And I was a first generation college student. So both myself and my sister were the first in our family to go to college. And also we ended up getting a PhD. So we sort of doubled down on it. I got my PhD in computer engineering. So as you see, I'm going from computer science to computer engineering towards the good part, right? In computer engineering from the University of Southern California in '98. I spent a couple of years as an assistant professor in electrical and computer engineering between '98 and 2000. And then 2000 to 2019, I was at Carnegie Mellon. Again, in electrical and computer engineering. Before coming, I was the associate head for academic affairs and the director of the Center for Faculty Success there. And like I said, from December 2019, I joined UT Austin, where I'm now a chair and a professor in the department. I'll talk about my research, but much of the work I do is in energy-aware computing, sustainable computing, and computing for emerging applications. And I'm going to talk about my research, but I'm also going to tell you how I got to do the research I'm doing and how I got to choose the career I chose. And I can focus more on one or the other if as you guys want. Um, what I have done recently, like I said, I had I was wearing multiple hats. My group, which is dubbed EnyAC, from Energy Aware Computing, and for those of you who are familiar, EnyAC, but with an I, not with a Y, was the first computer that has ever been built last century. Typically, I have 4 to 6 PhD students and another 4 to 6 maybe master's undergrad students, sometimes a postdoc or two. So right now I'm building my group here at UT. I still have students at Carnegie Mellon who have to finish their research. Like I said, until last year, I was also a director of a center in the College of Engineering at CMU, as well as associate head for academic affairs also there. And now I'm here. Sometimes I like to put some of the things that people may not know about me, but now you will. So I actually decided in 8th grade I would be a college professor, which is really early, I'm told. Because I have 3 children and none of them actually knew what they want. Some of them are past their 20s. They're in their 20s and they still don't know what they want to do. So they're still looking for their career path. But I guess it was a coincidence that I thought I would like to be a college professor, and then I ended up becoming one. And I think it's the best job in the world because I get to work with young and energetic people all the time. So, and I only had a real job for a very short period of time, and I'm going to tell you when. And I call it real job because it's an industry job, not an academic job. Like I said, I was a first generation college student. I majored in computer science, although all my life I've been a faculty in an electrical and computer engineering department. I lived on 2 continents, in 4 countries, and in 8 cities in the last 25 years. So the 8 is because now I live in Austin. But that's by virtue of actually being an academic. I was really fortunate to be able to spend my sabbatical in Europe. I also spent the summer also. So my sabbatical, for my sabbatical, I was at Technical University of Munich in Germany. And then the next year I spent time in France at in Grenoble at both the university and the institute there. And so by doing so, I was able to actually not just enjoy working with a lot of collaborators around the world, but also just have a chance to experience the culture in multiple countries. And as you've seen, I kind of moved around in US, and I'll tell you more. It's not just LA and Maryland and then Pittsburgh and here. Before that, I actually spent some time in New York at NYU for 1 semester. So anyway, I was the first woman to be hired at Carnegie Mellon in ECE, and the first to actually be promoted through all the ranks. And as you know, I'm the first woman to chair the EC department at UT Austin. So a few firsts there. Hopefully there's going to be many more after me. Being a department chair was never on my list. I was never looking to have this job. But I think I really enjoy and truly treasure the time that I can spend with my colleagues, with students, and we have lots of great staff that allows us to or at least attempt to do a great job in the department. So how I got where I am. That's me at 5 years old. Math was, I really remember that math was my favorite subject, even in elementary school. In middle school, I actually had to choose between going to a competition in art, a competition in creative writing, and another one in math, and I chose math. And ever since, I never thought, okay, I don't need to think what I'm going to choose because this is what I like. So then I ended up, although until high school, I thought I would just do math. I would major in math. And like I told you, I decided I'd be a college professor. But in in high school, I decided to switch to computer science. So I decided to apply for a computer science major rather than math. And I get to do quite a bit of math even now. So I don't think I regret, absolutely, I don't regret the decision. And the bonus is that I actually, I'm able to do real things and build things that actually help others. And that's me in 91. So that's right after I graduated college. What's interesting is that, like I told you, I was a first generation college student. I had not seen or programmed a computer, although I was a computer science major. And today, if you think about yourselves, your undergrad major was probably in a computing or science related kind of or engineering related discipline, right? You are now NEC, but I'm sure that not only you have seen, but also used a computer throughout high school, right? So this is actually many years ago. This was pretty common, although there were quite a few of my colleagues in college who had actually even majored in their high school. There was like a special track for informatics and computer science. So I actually didn't feel it was that hard. I enjoyed learning programming because it had quite a bit of, it was pretty, it was taught in a formal fashion, and but it was a good segue from more on the math side and going towards the engineering side. So I enjoyed that quite a bit. The way I learned to be a computer scientist at the time was actually different than anyone would do it today. And I don't know if this was done by design or just by virtue of the time that I was in college. But in my first year, we would program using punch cards. So this was in 86, 87. And it was a little bit behind times in Romania at the time, because in other countries, of course, you wouldn't use punch cards. But then by my sophomore year, we were programming a mainframe. So these 2 years actually were really formative in the sense that I had to figure out, or we all had to figure out how a program works or whether it works before running it. So you had to run it in your head, compile it in your head, and make sure it works, because you had to go again and punch the cards and run the program again, or you had to schedule time to run it on the mainframe. So you wanted to make sure you got a finite number of attempts, so let me put it that way. So you had to really be really good in figuring out if this works. So by the third and fourth year, we got to have access to personal computers. So this was this was, I guess, pretty much in the 80s, that what everyone was using. And that on top, if you can see, that's like an 8-inch disk that we used to use for storage. Many of you might be too young to even remember that. So yeah, this was late 80s. And then in 91, I graduated. So just a little bit of context before. So I started in 86. My degree in Romania was a 5-year degree, a 5-year engineering degree. Now they switch more towards a bachelor's 4-year degree, followed by a master's. But at the time, you had 5 years in school for your degree. In 89, when I was in my 3rd year, this is when Europe had started to open up, I guess. So by end of it, 1989, pretty much all of the Eastern Europe, so Romania was part of the Eastern Bloc of, I guess, communist countries. But then by December 1989, everything was, I guess, all the boundaries had fallen. And this is an image from the Romanian Revolution from 1989, more than 30 years ago. I mean, you can see here some, I mean, I have to admit that I was in one of these trucks when the revolution started. Many of the young people were really happy that the regime had ended. So that actually meant that people could now apply for grad school outside of the country, so internationally. So I held a software engineering job for 6 months. That was the only time I actually have been in industry. And then became a junior lecturer in my undergrad institution. And that's when I decided I'm going to go to grad school, and I'm going to apply to a few schools in US. So in 92, this is all I did, right? I learned a lot about the various tests that people, and this was unheard of because we've never had multiple choice kind of testing in Romania. Everything was open questions, open-ended questions. So standardized testing was unheard of. And I remember it took a while to get used to it, but eventually, I managed to do it. At the time, all applications were paper-based, so nothing electronic. And I remember the way I chose the schools I was going to apply. I thought, okay, I'm not going to apply here because I'm not good enough. So I actually excluded many schools just because I thought I wasn't going to be good for that. So I never applied to any of. I don't think I applied to UT. I'm pretty sure I did not. So my criteria for applications was basically, where do I know people who are successful coming from the same school as I was? Because I thought, okay, they're probably more open to admitting PhD students, and I wanted to do a PhD. So PhD students from this part of the world. So that's how I chose where to apply. So not many schools. And of course, it was a daunting task because many of the applications that, they were sent ground mail. How do you send ground mail from US to Romania? I guess on a ship, or I don't know, because if it's not by air, I don't know how you would get on a transatlantic kind of destination. And I remember receiving applications, many months after the deadline, just because they didn't realize that the address was nowhere near reachable by ground. So how I managed, I actually kept a bunch of lists and trying to figure out the best way to determine how I can get to a school where I can do or get a PhD degree in the discipline that I wanted. And at the time, what I wanted to do was, so this is late 80s, early 90s. So artificial intelligence was, I guess, experiencing the first wave. The second wave is obviously now. And I thought, I want to do AI, and I want to do natural language processing. Well, I never got to do that. But I did learn how to put together a good grad school application, not because I did it at the time, but because I learned from my own mistakes. And you're already are in grad school, or you have even completed it, for those of you who are postdocs. But I found the best thing is to be prepared. So I was lucky that I already had a thesis that I had worked on, and people on my committee were actually my letter writers. So in US, for example, or even in other countries, having undergrad research experience is the way to accomplish that. I took whatever tests were needed. Many schools now are GRE optional, or they don't require GRE this year for sure. And they're actually contemplating whether that should be removed, because GRE is really not the best indication for success in grad school or even in a PhD. Putting together a compelling statement of purpose. And I learned a lot about how to write or not to write. I know my first one was not a good one, but then I learned how to do it in a better way. And coming up with a list of schools and potential advisors. And I did not do it back in Romania, but then I did it the second time, and I'm going to explain to you how. And then get a good set of letter writers. These are actually these last two, or even three, are good in general, not just for grad school, but also for if you're applying for a faculty position. Same thing. You want to have a good way to put together a statement of research, teaching, or diversity. Also put together the list of schools you want to apply to, and also get good letter writers. For grad school, definitely best in class is not sufficient, because you want them to talk about your research abilities, and for faculty, you want them to talk about your ability to actually be a potentially a good faculty member. And of course, you need to apply. So about my grad school journey, so I did apply from Romania. I landed in computer science at the Courant Institute at New York University. I remember I did not apply. I don't think I applied at any top 10 school. Like I said, I did not believe I'm good enough, so I did not apply. I applied at mostly top, I guess, 11 to 20 and below, where I knew that there were people with the same schooling and background as me. So NYU was one of them. For the first semester there, so I lived in Greenwich Village, which was quite a culture shock. Because as you know, NYU and they're in the southern part of Manhattan, and it's a really lively place to live, also very expensive. I remember I was paying 2,000 for a room in an apartment, so that was a lot, and that was in early 90s. I actually, for the first semester, I TA'd a class, programming languages, and the instructor was Alan Gottlieb, whom I knew from books. And you probably know of him if you're in Access, or you know about, I guess, high performance computing. He was well known at the time, but he was teaching programming languages. I don't know why, but I TA'd for him. And I also took a bunch of classes from well-known people at NYU. One of them was Richard Cole, who was teaching algorithms and data structures. Also operating systems. I was taking operating systems the second time, right? Because none of my classes that I took in Romania would count, so to speak. They would not translate. This was an honors class. So I took it again, and again, operating systems, I think it's probably one of the hardest. So it wasn't a bad idea, actually. But then after one semester, there were multiple reasons why I wanted to move. First, at NYU, I was holding a TA position. I did not have a research assistantship position. Second of all, also personal reasons. So my husband was already at USC, so I did apply at USC, University of Southern California. And I was admitted in computer engineering. And I remember this is when I did it the right way. So I contacted people, I contacted potential research advisors. I realized that already by then, so this was late 93, already by then AI was kind of starting to diminish in importance. People weren't really interested in AI and natural language processing. So I sort of shifted, and I realized computer engineering is actually it has a lot of the things that, interesting problems, and really that's how I ended up choosing. And I was ended up working with Masoud Pedram as my research advisor in computer aided design, or electronic design automation for integrated circuits and systems. So I remember I first started looking at formal verification, but then moved to low power design and energy efficient computing. So that's how I ended up doing what I'm doing. And I think that was the best decision I did. So moving from computer science all the way to EC, eventually seeing the light and finding your place. And I don't think it's I'm the only one, because if you look at the many people we have in our department, many faculty actually they do have CS degrees, but many have physics degrees or math degrees. So you can come, your path doesn't have to be linear. It's all EE or EC, right? So it can be, you can find your way. It can take time to find your way. I spent 5 years there. So I basically fall 93, I was at NYU, but then end of 93, I moved, started spring 94 at USC. I took some interesting classes. One of them was Seymour Ginsburg, who was teaching formal languages. But my dissertation committee, and this is an advice I would give everyone, is try to get interesting people on your thesis committee, because they will you will remember the types of things that they will ask you just to be on your committee. So I remember, I believe I set an appointment with Mel Brewer, and Mel Brewer, his area was testing. Unfortunately, he passed away a couple of years ago. And he said, I asked him if he could sit on my dissertation committee. And he said, well, you have to tell me what you're going to do in your thesis. So I set an appointment, and then it ended up being like a 2-hour mini defense, right? So I had to explain everything I was going to do before he would accept my invitation. And you might think this is extreme, but it actually was a very good way to prepare me for what I should actually put in my thesis. And this was, you're supposed to put the process. I know UT has a different process, but this was, you had an initial exam, a screening exam, which was oral. And for those of you who have heard about different candidacy exams at various institutions, this particular exam was comprised of 7 oral exams, 1 hour each, scheduled across 2 days. And I had passed that in my second year. And I remember, again, operating systems, right? I was in computer engineering because they had a major for PhD in computer engineering. So I had to take the exam in operating systems. And everyone, I mean, 90% of computer engineering PhD students would fail the first time because the professor who was giving this exam was in computer science and his standards were really high. So, you know, I thought, okay, I'm not going to pass this. I'm going to have to take the screening again. And I remember going to the exam, and of course we start with questions related to OS, like barriers, critical sections, things like that. And then he starts asking about how would you implement these things? What data structures would you use? And then from there, he started asking, well, can you write the code for this? How would you implement it in C? Or how would you, what's the complexity in big O notation for inserting, deleting, sorting? And I had done that many times, right? Because I took the class, yeah, and I had been a computer science major. So he was very surprised that I knew all the answers, and I passed. So I guess I was one of the lucky ones. I'm pretty sure they changed their screening exam now, but you were supposed to put together your dissertation committee after you had passed this and like a year or 2 before defending. So the proposal, it was called qualifying, which I think here the qualifying is slightly different because there is a proposal review, like a thesis review later in the program here at UT. But to be able to have a committee formed, you will need to make a presentation and propose the thesis topic. But before I even proposed it to Mel actually wanted me to describe what I was going to have in my thesis. So I did not regret that he grilled me, because that prepared me to, it showed me that I actually have to be more rigorous in everything that I was doing. And Michael Arbib, he's actually a guru in neuroscience. And having an external member is really important. I took a class with him, and the reason I actually chose one academic as my external committee member is because I was interested in academic position. So this is actually one of the things that you might want to think about, depending on where you want to land in industry or academia. You might want to think about how you choose your dissertation committee. And it was a colorful committee, right? Because they all had different backgrounds, they all had different ways of interacting and requirements. Yeah, it was, if you can choose, you know, people that you are proud of saying, oh, I had this person on my committee, then I think you should go for it. And I think we have a great set of faculty in our department, so go for it. We have many National Academy of Engineering or National Academy of Inventor members. We have one Emmy Award winner. We have so many IEEE fellows or ACM fellows. Just try to get the best of committee that you can. And of course, you should work with your research supervisor, but do your research first. Try to see who would be best. So what I found as most useful in moving forward with a PhD is, first of all, find a good, if you can, great research advisor. I think it's really important, because that is going to, having a good relationship with your advisor is actually key to success. Also a good research topic. The fact that many times, I work with my students, and many times it takes some time to find the research topic, but it's really important not to settle just for anything that, okay, not the low-hanging fruit. It's okay to have a few low-hanging fruits once in a while, but your thesis has to bring new knowledge, has to advance, and have an application. We are engineers, so we have to do something that counts. We have to make things that help others. If you can, don't take a full TA position, because you're not going to have time for research. In my first semester, in my first semester at NYU, I was just a TA. I did not even attempt to do research. I was reading some papers, but and there was no expectation from me to do that, right? So I did not even try. At USC, I had a grader position, so I was grading. It wasn't as much effort, and I was able to do research. And then over the summer, I decided to not take an internship. I had an internship offer at Intel, and I said no. And I stayed over the summer and ended up having a paper published. So presented in November, so within less than a year from joining, and then again another one the following summer. So I think it's really important, if you can, if you see you have the momentum, just go for it. And maybe it's okay to say no to this opportunity. You have this shiny internship at Facebook. Maybe you can say no, because maybe it's going to come again. And also I don't think your advisor, I was fortunate that I did not have to do that, but I know others were at the time. This was early 90s. I'm hoping that's not a practice anymore. You can't do, if you're a TA, if you're a full-time, you're TAing, for 20 hours a week, there isn't any time left, because you're also taking classes in the beginning. There's no time for you to do research, right? So try to balance these things, and hopefully you find the best way to balance these. If you take a TA, or just take classes, finish the coursework, and then try to secure a graduate research assistantship. So this is kind of, it may be seen as a dichotomy, but I think you should try to be both broad and deep. And what I mean by that is, you want to be broad in the sense that your thesis cannot be just a little thing that enables maybe one algorithm or one design somewhere. And you want to be broad in the applicability of your work. So does it generalize? Is it still going to be applicable 10 years from now? And if not, is it because of the technology, or is it because of the limitations of the work? So you'd rather be in the first category rather than the second. And also you want to be deep, because it has to show that you look at the problem fully and completely understand the context, not just the big picture, but also the context for the application itself, for the where is it going to be used, right? And I think there are multiple tests for that. So you're going to do your work, you're going to publish in conferences or journals. You're going to present, you're going to have a dissertation committee who's going to tell you, this is great, this is maybe not so great, you have to work, and just don't do that, right? But I think it's not a contradiction. You can achieve both, because I think that's how a thesis is supposed to. I don't think you should sweat the grades. I actually was surprised when I came at UT, the requirement for the GPA here is 3.5. CMU had a 3.0 GPA requirement. I think most schools have a 3.0. Maybe Illinois is 3.5, and maybe in one other. But to be honest, I don't think the grades are that important. Yeah, they're important. It's important to take the courses and get the knowledge, but really from the perspective of where you're going to end up, industry really doesn't care much about grades. They only care about the expertise, skills, and the breadth that you're bringing to the table. And if you're looking for an academic position, no one checks for your GPA, right? So whenever we search for faculty candidates, we look at other things. We look at their potential and capability to do research, to teach, their interest in both research and teaching, but also ability to contribute to the departmental culture. So I don't, to be honest, I mean, if it were up to me, I would actually change. I probably need to get the faculty to vote on, but I don't know if 3.5 is needed, to be honest, because it doesn't necessarily reflect the skills that are needed at the end of a graduate degree. One thing that's really important is to work with your advisor, and not just your advisor, all your informal or formal mentors, to create your network or grow your network and connections, because that's really important, especially if you want to get a job after you are done with your PhD or a postdoc. And the type of network you build should also reflect your interests, right? So if you want to get a job in industry, your network has to look a little bit different, perhaps, than for a job in academia. And like I said, try to be thoughtful in putting together your dissertation committee, because the external members can, you know, they're going to see your work, they're going to see you in action, then they can write letters for you. So external members, if you can get someone outside of UT and someone that actually is in the same kind of place where you'd like to be, either so it's a company for industry or another institution, other university, if you're looking for an academic job, I think this is how you should go for it. And of course, on top of this, don't forget, you should have your own life. Make sure that you continue to do the things you enjoy. So your friends and family and even your lab mates or student organizations like this are essential. You should not just do your work and do your research, take the courses, and that's it. It's really important to have a life outside of work. Now, about my research, and actually before moving on, do you have any questions? Because I'm going to talk a little bit about my research, and then we can have more questions.
I think there was one question in the chat, actually.
Oh, I didn't see the chat.
Yeah, it's all right. So the question was whether you were a Master of Science or PhD student at NYU.
I was a PhD student. Okay. Yeah. And I never got a master's in US. I went all the way from a 5-year degree that I got in Romania. I got a PhD from USC, but I did not get a master's, and you don't need one. I think I tried to, but the way you counted, because my PhD was in computer engineering, I couldn't double count something. So my master, to get a master's, I would have needed to take more courses. So I didn't want to, so I just did more research rather than take more courses. So I don't think anyone cares. If you have a PhD and a bachelor's, no one cares if you have a bachelor's in between. Sorry, a master's in between.
I actually have one quick question.
Yeah.
Maybe up to research and PhD and advisor. So, I mean, managing student or managing your research advisor, which is tougher, would you think? And what kind of recommendations maybe you would give to PhD students on not just being advised, but actually trying to manage the advisor by themselves?
You mean managing your relationship with your research advisor, or?
Yeah, but also like being open, trying to propose your own research. You know, some advisors may be reluctant to do that and some not.
So actually my philosophy for that, and that's exactly how it worked for me when I was a PhD student, is the reason I'm admitting these students in my group, the reason they are in my group is because they do have an interest in the topics I work on, right? So, you know, I have these other projects that my students are working. This is how I see these evolving, and this is how you could help. So I give them specific examples as to what they could do. I also tell them sometimes that works. So this is a great way for them to get started by working with someone who's a little bit more senior than them. But many times they say, actually, I want to propose my own. and they say they propose their own topic. Sometimes I propose a new topic that no one else is working on, and that may be a little bit more risky, right? Because they're going to be the only one working on that. And sometimes it's research. Sometimes it doesn't pan out. So I've done all of them. I think the most successful way is when students work together with more senior students. They learn in the infrastructure, they learn the field this way, and then they come up with their own, and then they have their own first author projects. In my case, it was, I knew my advisor was doing CAD in a very hot area. I came up with an idea that, they were looking at this. I worked on it over the summer. So just one semester after I came. And actually we submitted something. I was part of a project. I became part of a project really early. So we submitted something in April. I had joined in December. So April submission, I already had a paper. I was a second author, but still I had gained experience just by working on something for 4 months. And then, over the summer, I did more work and had something ready for submission in September, October. So I think it depends on your research advisor, but I usually allow my students to propose their own topics. Typically, I only had one case where one of my students was trying to publish in an area which was really crowded, and I told him it's not gonna work. So he tried like several times, and then I said, it crowded, and also you couldn't do much. It was everything we were doing was incremental. So after 2 or 3 tries to submit something that kept getting rejected, I said, okay, now you're gonna do what I tell you. This is the topic. And he was really successful and went to work for AMD for many years. Now he's at Tesla. I don't know if he's moving to Austin. I know he's in Bay Area, but yeah, sometimes I do allow students to explore whatever they'd like to. Okay. Does that answer the question?
Yeah, definitely.
Right. So here's my research. So as you know, this is Moore's law. It allowed us to be where we are, and this is actually even going now. This cuts off at 2005. But the idea here is that there's another trend here where we are progressing in terms of the compute power, but this comes at a cost, right? This comes at a cost of power density. So this is where my role comes, or my research is on energy efficient or energy aware computing, because computing energy does increase at the same rate. So this is where looking at thermal impact, thermal design power, aging, everything that comes from that. We have the laws of physics that don't allow us to run our chips too hot. So basically what happened was around that time, so if we expand the previous chart, this is exactly the same chart. Around 2005, what happened was, was that this trend pretty much stopped. So the power was capped, but the way it was capped is by, if you see here, switching to multi-core. So this is where I've done a lot of my work in energy efficient computing, in multi-core systems, chip multiprocessors, power management for those, as well as looking at process variations and other things. But the goal would be obviously to get to the brain equivalent. So this is why now people talk about machine learning and AI, because computing enabled machine learning and AI, but at the same time, we want to be able to get the same compute equivalent that the brain has. I don't think we're there yet. And obviously this is probably when I'm going to be long retired, but we do want to be there. So my early work actually had to do with power modeling and trying to come up with good abstractions to go from low levels of abstractions like circuits and gate level all the way to system level, because typically, and this was possible because as you know, we are able to package functionality in an abstract way and in composable and predictable models. So typically the way the design works is you start with a system level view, you refine it. So this is an example of a super superscalar processor. And then gate level, obviously, a transistor here would look like this, and technology device. But the thing is, typically, the highest impact decisions happen at the system level, but the most accurate models are when you're closer to the physics, right? Because that's where the behavior is. So the problem is, how do you marry these two? Initially, my work was on modeling. So I did a lot of work in probabilistic modeling of dependency. So this is the journal paper that actually, it took us 3 years to publish, 4 years to publish it. The original paper that we published was in '94, right? So this is my first, but we extended it for a journal. And then for my thesis, I actually worked on information theoretic measures for power modeling. But then more recently, like I said, you have process variations, you have more complexity, so you have to look at chip multiprocessors, and at the same time, you have heterogeneity, right? So these are some of my more recent works that I worked until maybe 4 to 5 years ago. So again, chip multiprocessor and power efficiency. But now what I do is hardware-aware machine learning. So I guess I went full circle from me wanting to do a PhD in AI, deciding that it's not going to be good because there's no interest at the time. But now I am looking at machine learning and AI, but from the perspective of the hardware that drives it. And the way I like to pose it is putting the machine back in machine learning, right? Because we sometimes forget that machines made possible machine learning because of the progress that we've seen in computing. So this is an example that I usually give when trying to explain the kind of research I do. So if you have a set of smart devices that are off the network, they're not connected. If you ask some very simple questions, 100, if you ask like your digital assistant, how to divide it by 2, your name, or what is Apple, the answer is invariably, I'm not able to help you right now. Please try me again in a bit. The reason for that is all of these services, speech recognition, and these kinds of tasks are all run in the cloud. And there is no reason why they couldn't be run locally if we think about better ways to implement those applications and better ways to implement or design the hardware that supports them. And I'm sure you know that these are everywhere. You know, if you have a smart device for your autonomous driving car, your smart home, mobile wearables, VR, AR. These are all powered by machine learning. And of course, deep learning is the craze, but it is not energy efficient. In fact, it drains your battery lifetime very fast. And the reason for that is these applications are very expensive. So when you run them in the cloud, you don't care. You only care about the response time, which is sometimes not good because you might have real-time constraints, especially when you do video or object detection for video recognition. So ideally, it would be best if you ran them on device. And this is the example with Siri, right? So this is where my work has been recently, but it's hard. And the reason it's hard is that deep learning is hard to begin with. Finding a model that has a good accuracy has to, look at all of these different different models with different hyperparameters. And of course, you would like to find this one here, which has the lowest classification error. But at the same time, if you look at the hardware, and this is energy, there is an even higher spread. So you not only want the lowest error, but you also want the lowest energy, because this model here is very expensive. So the question is, how do you find this best configuration? That's pretty challenging because it takes a long compute time. And there was a paper last year that showed that language recognition models using BERT, which is one of the most well-known machine learning models, to train a model like that actually requires more energy than an East Coast to West Coast kind of flight. So it's really expensive in terms of energy. So what we do currently, we look at 3 things. First, we look at modeling, and we model the hardware, and we also model the machine learning model. So one is the hardware, and it's just an example. I picked the Qualcomm, but it can be any hardware. And you model the machine learning model running on it. And then you have constraints, maybe power, maybe latency. And also you want this model to be accurate. So the first one is modeling. And neural power, you can find it on GitHub if you're interested. The second part is doing architecture search to find these configurations that are good for both accuracy as well as latency, energy, whatever you want, right? So it's neural architecture search, or NAS, can find in hours rather than days this best configuration. And the last piece is, once you have this model, can you actually optimize it further? And this is where we try to compress these models such that they fit from a large compute device to a tiny one, perhaps by quantizing, compression, optimizing the bit width. So these are various approaches, and I put some references here if you're interested. But the idea is that you can get orders of magnitude better energy in much smaller area and storage, and not lose much accuracy. So this is really promising, right? Because it takes you to something that's called machine learning systems on chip, but I like to say machine learning systems on the chip, because they can be really tiny in terms of storage, as well as compute power. But you can get benefits in terms of how fast you find the design, how efficient they are, and also how optimized the final model is, with applications everywhere in mobile and IT. So I think this is where I think it's the best, EC is the best place to address this, because we do have expertise in the vertical system integration all the way from devices to the system and even the software, as well as great expertise in machine learning. So it's not just me, my colleagues are also doing a lot of great work in this space. And I'm looking at mostly IoT, so on-device intelligence, but many of our faculty look at cloud, for example, or the interaction with the cloud. So if you were to implement this, even though your devices might be off the network, eventually they would be able to run everything locally. So if you would ask my smartwatch, what's my name, it would be able to give you a proper answer, meaning it knows my name, it should know my name. So, and that the task is run locally. So yeah, that's what I do currently in terms of research. I've been very, I just gotta put names. I don't want to, but these are some of my students. That many of them are in academia, some of them are in industry. So, for example, he's at Google. He's in Taiwan as an associate professor. Siddharth is at NYU, associate professor. Sebastian actually now works in energy trading, and Natasha, she's a assistant professor as well. But I have many of my group's alumni are in various places in industry as well as academia. And I think that's the best job that one can have. So what helped me? Like I said, try to balance your career and your personal life. And one thing so this is something that my son left. It's a Post-it, right? That he's left on my laptop in, I want to say it was around 2005, 2004. So he was maybe 9 or 10. And this says no more SIG-DA, DAC, ICGED, and ECE. So ECE was the department I was in. I've always been in ECE department, right? SIG-DA was the professional society I was part of, and DAC and ICGED are conferences that I was always going to. And so this is an example of, try to not lose the big picture, right? You have your personal life as well as your professional life. And you need a support network, make sure you build one. And ask your advisor to help you build a professional one, but your friends and family should help with everything else. Prioritize. Many times we're looking to do what's urgent, because you get an email from whoever saying in capitals, urgent, need this today, but it's really important, right? So try to push back and say, it's really, try to prioritize the important from the urgent. And then finally, don't rush into decisions. This is a book I really liked reading, Thinking Fast and Slow from Daniel Kahneman, and it talks about how we can make sure that our decisions are, think before you act, right? So always try to think about the impact that your actions might have. Impact is more important than intent. So it was a great journey. I did not intend to be an engineer, but I'm really happy I found engineering as my job. You should also consider becoming an academic, because I think it's the best decision I made. But if you really are interested in navigating an academic job, that's probably a separate presentation. And that's it. Thank you so much. Oh, I think there are some questions, right?
Thank you for your talk. Yes, we have definitely a lot of, I believe we should have a lot of questions.
Thank you. So the question is, can I think your research is about SysML, which I believe is intersection of systems and machine learning? And the answer is yes. Actually, there's a conference that used to be called SysML, but because of copyright issues, now it's called MLSys. And actually, the program chair for that conference is Alex Dimakis, who is in our department. So we have great representation there. Yes. So I'm doing systems for machine learning, as well as trying to adapt or make machine learning as applications more amenable to be run on hardware devices that are, like your phone, or something that you wouldn't think would be possible to run a machine learning application. Any questions? Don't be shy. I don't know. Oh, we're out of time, but
I guess that's all right.
I can stay.
I have a quick question. I mean, you mentioned that, already by the 8th grade, you decided to be a professor.
Yeah.
Was there any time, have you thought of quitting academia, going to industry, usually, for more money perhaps, or for some other reasons? Were there those situations, and how did you maybe, overcome them, still decided to still be in academia?
So when I was a PhD student, I had 2 offers for internships and I turned them down both times. I don't know why I applied, but I did. And then I decided I'm not going to take them. When I graduated with a PhD, I did think about applying for, at the time, you still had research labs. So Bell Labs still existed. IBM had research. Of course, Facebook and Google and others did not exist, which are now the equivalent of, having research labs. But when I was in academia, I guess the one time when I thought I considered industry was, so I was at Maryland for a couple of years, and actually my husband was at University of Minnesota, and we did consider for a while, what if we just, forget about academia, because we were in different cities, and just try to find a job in industry in Bay Area, because, this was around, this was like the .com boom around 2000, right? So, but then I realized, and I think we even, Intel, so the strategic CAD lab at the time was hiring quite a bit. So we did consider doing that. But the person who was trying to hire us eventually went to academia himself. But I did not, we didn't really, I didn't consider it at all. So, and after that, I was approached several times by people in industry, and there were cases where, even now it's actually pretty hard if you're if you need a lot of infrastructure to run your research, which is typically the case in computer systems, or especially if it's related to machine learning, because you need access to a lot of computers resources. You might be tempted to go to industry, but what I would miss is, even now I miss teaching because I don't teach. So I'm hoping to get back to teaching. But at the same time, interacting with students is really, I really enjoy working with students as, graduate students, and also having students in my class, which I think, you have the privilege of working with a perpetually young set of colleagues, whereas in industry, you're aging and everyone else is aging, I guess. So I don't know. I feel like I get energy being at the university rather than in a company. There is a question: how do students who have had a significant undergraduate research experience adapt themselves to a structured research program? So I guess it depends. If you have a lot of undergrad research experience, it's not going to be hard for you to take on a research project. It might take some time to adapt if your experience or background is in a very different area. And I did have, so one of my PhD students actually had majored in physics, in applied physics. He was a PhD student in physics, and then he switched to engineering. And I was very concerned that he wouldn't be able to do, it will take quite some time to adapt, but he actually did extremely well. Because of his applied physics background, which is largely theoretical, he, everything that had to do with math and problem formulations and optimization, he was great. So he started by doing energy-aware computing, looking at process variations, and near threshold computing, which is actually close to physics if you think about it. But he moved to chip multiprocessors and multi-core systems. And then towards the end of his PhD, he did the work on neural power. So he actually put together the modeling framework that we have. So he did basically got a master's in machine learning along the way, because at CMU you could do that. And now it's harder because you can't double count courses anymore. And then his job, he works at a fintech company, a financial technology company. So you just have to be open-minded. You don't know what life is going to bring you. Okay, so one more question. What is your criteria to select your PhD students? So I don't look at GREs. I do not look at grades. The only thing I do, I look at the grades, but if I see that, it's consistently good in the things that matter, that's fine. If I see that, there's like a dip in grades, especially in courses that might be important, I ask what happened. And sometimes there's a very clear reason. What is most important for me is actually having research experience as an undergrad, or if you have a master's already, as a master's student. And also the ability to have your letter writers articulate that. So if you did research with someone, the person you did research with should write the letter, so I can actually take a look and see how it worked. And there's one question: were there any specific challenges you faced as a woman in your grad school and academic career? Do you have any advice for us women? Sure. I do remember in my when was it? I think it was my first year in undergrad. But you asked about grad school. Okay, grad school. Oh, grad school. Oh, of course. But it's not as bad as anymore, right? So sometimes when especially during the interview process, because job market twice, right? So right after PhD, when I got my job at Maryland, and then again in 2000 when we were trying to find jobs together, and we did eventually. So even in 2 years, I've noticed that things were getting better. But one of the things that at the time was, and we were both my husband and I were interviewing, and I could see his experience was different. So sometimes people would ask things that you're not supposed to ask, like, are you really serious about this, right? Because they believe that sometimes women would have a different trajectory, or would not be as serious because maybe they're only interested in other things, like more family, or other things that may disrupt your career. obviously, I think now, at least in our department, we are very careful in how we interview our faculty candidates, and we for sure don't ask these kind of questions. There were some interesting things that so interview process is one thing, but then throughout my career as an academic, it is a little bit. I mean, the people make assumptions, but I think most of the time, because I'm friends with them, I see them all the time at conferences. So I would go to the conference. Maybe I was the chair of the conference, and then they would ask me, "So, who takes care of your children when you're here?" And I said, "Well, whoever takes care of them when I'm there, because I'm not taking care of them. They're in school, or there's someone who, you know, you want to have a support network, right? Even regardless, as a young researcher, you want to have support. If you have children, you want to have uh, a daycare, and you want to have someone who comes after hours in case is needed, or even not after hours. If your kids are sick, you want to build that infrastructure, right? So it's not like you have to take care of them, but of course you need to find the right support. In my case, it was when I was a student, because my oldest son was born when I was a PhD student, so my family actually helped quite a bit. And both my mother and my mother-in-law actually came and stayed with us for months to help with our son, because there was a wait list even then. There's a wait list everywhere for getting access to good daycares or schools, right? Uh, but I think there's more understanding now about these issues, and there's more support. So, and I think at UT there's a lot more in that as well. Throughout, most academic institutions are, and I think major companies also have quite a bit of support. There's a support for a family leave, like parental leave, not just for women, but also for men, which I think is really important. So recognizing that family is important is really more widespread now. Okay. Any other last minute questions? I don't want to hijack your time, but I'm happy to stay.
Yeah, you mentioned that you switched from computer science to ECE. So how did you build background for conducting research in a new area?
Yeah, so that's a great question. So I guess I mean, it wasn't hard for me, because actually in Romania, the computer science degree was it was more like an EECS. So your first year was just math, physics, chemistry. And then I did a lot of system theory, numerical so discrete math, so both from the math side or computer science side, but also from the EE side. So I remember I took the microelectronics class. There were 2 in a sequence. It was a really difficult class, and they used like a scale of 1 to 10. And I was really happy that I got a 9 out of 10 on that, because it was really difficult. But I did have the undergrad background. So the first 3 years were the same for everyone. And it was like a double ACS. You did both EE and computer science. In your last 2 years, you would choose either, you go more on the microelectronics or automation, control, signals and systems, or computer engineering or computer science, which is what I did. But then I had the background, and I really, when I started doing research in EDA, it was a lot of, EDA is algorithms for building circuits, right? So really the job title for many of the people who did a PhD in EDA was a software engineer, because you do write code. You have to write, the cadence design flow or the synopsis tools. That's software. You just need to understand the hardware that you write it for, right? But it wasn't So I took whatever classes I needed to ramp up more. So I took VLSI design, which I barely took in Romania at USC. I took two versions of that, and then computer architecture twice, both basic and advanced computer architecture, because although I did take it in Romania, but it wasn't really the right, it was more like computer organization and design, not computer architecture. And I remember my TA for computer architecture at USC was Luis Barroso, who's one of the VPs at Google now. So I have many friends from USC who are in top positions, but they all migrated kind of to these kind of companies that now do both hardware and software. Yeah. So this is why I said broad. You want to be broad, but hopefully you're building that breadth, right? So you have to be open to not just look at what you've done as an undergrad or what you do as a grad student. You want to be as broad as possible, because who knows what's going to bring, what the future will bring. I'm not saying in terms of job security, but in terms of interesting problems to solve. And it would be a pity for you to not be able to be part of that. Yeah.
All right, I guess if there are no more questions, thank you very much for your fantastic talk today. This was really great to connect with you and have your perspective on so many things.
Sure.
Yeah, thank you very much. And I guess we should continue with those series of talks in the future.
Absolutely. Thank you. Anytime, please feel free to contact me. I'm happy to give you advice, or, happy to help you navigate whatever path you're deciding on. Thanks for the invitation, and have a great rest of your day.